So good afternoon, and thank you for digitally attending this presentation of our Software Center project. In this project, we are looking at the diverse development artifacts used to describe, design, or implement the same system, focusing mostly on software and system models. And in particular, we aim to manage inconsistencies between those different artifacts. So the overall long-term goal that we have defined for this project is to provide effective support for consistency management for industrial system and software engineering practices. And this comes mainly from the observations in our partner companies, where development artifacts at high level of abstraction, like system models, denote the system design, and in parallel, development artifacts at some lower levels of abstraction, like source code, denote the final implementation. And you want those artifacts to be in sync, so not to contradict each other. In such development settings, the development cycles are typically long and kind of rigid. And to increase the agility of these modeling practices, as is part of the goals of the software center companies, then one aspect that needs to be improved is to enhance support for inconsistency management across different artifacts. And this is one of the results of some research that we have done earlier in the sprint and presented last year. So of course, this management should be done still with the understanding that inconsistencies are inevitable during software development, and that complete and automatic resolution is not really possible, nor desirable, because we want to be able to create placeholders or other things that are not entirely complete yet. We don't want to be restricted in the development. So one of the challenges of this development scenario is to manage the consistency between these different representations of the system. And in earlier work, we have presented a lightweight approach to consistency checking in a kind of generic case. And the idea is to represent artifacts in some common structure and then apply various types of checks on them. So in a bit more detail, we create transformations that transpose the representation of the artifacts to the common representation, and then predefined checks compare the common representations. So here models MA and MB, conforming to two different languages, potentially LA and LB, are transposed to representations TA and TB that conform to a common tree notation, this TN. And in the paper that's cited here, we showed this approach by implementing it as a plugin for a continuous integration pipeline. And the approach is lightweight in the sense that it requires little user interaction to define the consistency checks, because you only require to point to which elements should be consistent with each other at a high level of granularity, of a high level of abstraction. So I've so far talked about generic kind of artifacts, but as I said in the beginning, we mostly focus on models. So in our industrial partners, they are creating system designs in SysML models and then implementing that design in code, but possibly also parts of it in hardware, so it's not all just code. But in general, of course, the system model can contain several different types of information, and it can also be expressed in different languages or formalisms. So now we look at SysML, but it could also be EastADL or maybe in UML with some additional requirements in some separate tool. And the same holds for the implementation, which can also be represented in different ways. For example, using software models in Simulink or AutoSAR or something like that. And from which then code may be generated or manually created, as is in our case. In this work, what we are focusing on is a SysML model and then implementation in C or C++ code. So we have, during the past sprint, we have considered two different aspects of this consistency checking problem between a model and source code. The first one, together with Saab, revolves around establishing a consistency checking mechanism within an existing MBSE development setting. And there we need to deal with existing artifacts and bridging the gap between the model and the code. And the model contains, of course, a much more abstract view of the system. It doesn't contain all the details that are in the code. And so then the main difficulty in practice is then to match parts of the system model to corresponding parts of the code. So we need to know which code parts implement which model elements. And the second considered aspect is in the context of modeling software systems that are comprised of software components. And those components are a good way to separate the functionality and enhance the reuse of parts of the model and the implementation. And the challenging thing is then to evolve the system, because it can be, the overall model can be reused in large parts to describe different variants of the same product, containing different selections of those components that it is comprised of. And at the same time, the variants are subject to incremental change through time. So there is a kind of two-dimensional aspect to it, where both the models are maintained across different variants and also through time throughout different revisions. And to make things even more worse, the individual software components, as well as their configurations, so the way they are combined together, also exist in different variants and throughout different revisions or releases. So in this sub-project, we focus on devising means to appropriately model these kinds of systems and enhancing existing simple consistency checks to make them aware of different variants and the revisions. So that concludes the introduction of the project context and its constituent parts. I will now go through both of the sub-projects and discuss in a bit more detail what we are trying to do and what we achieved so far and what we plan to do during the next sprints. So first in the Saab project, in this scenario, several system engineers work together with a dozen or so software engineers on the same system. And the system engineers are mostly concerned with capturing the intended system design in the system model that is then later handed over to the software engineers to be implemented. And the model is the core development artifact, but also functions a bit like documentation, and it contains the structural and the functional design of the system. The functionality is decomposed into function blocks that are then further implemented by smaller components. And the model also captures the allocation of those components to either software or hardware. But do note that the refinement of the system model into implementation is a manual task, because of course the model does not contain enough detail to automatically generate code from it. The system model is described using SysML diagrams. And here the image shows a bit of the makeup of that. So each function block is represented by a block in a block definition diagram containing a combination of system components. And that is supplemented by an interface described by SysML full ports. And each system component is described by a block in the internal block diagram corresponding to the function block that it is contained in. And the system component contains again attributes and operations and signal receptions in the form of proxy ports. And each operation defined in the system component is defined with an activity diagram. And then each system component contains a state machine defining its behavior. So you can see that there are a lot of different diagrams expected in the model that could contain interesting information for us to check if they are consistent with the code. So the motivation for automated consistency checking in this scenario is that not only the implementation should follow the design, which is kind of the obvious way, but also the design must accurately reflect a delivered implementation in order, for example, to eventually allow for reuse of parts of the model or the implementation, but mostly for maintenance reasons for projects with extremely long lifespans. So doing this checking manually becomes kind of infeasible because of the size of the model, because it generates hundreds of pages of documentation that then need to be manually checked with the code. And that kind of manual actions would also kind of inhibit introducing more shorter development increments. So we need to automate some form of consistency checks, and also these requirements show that we should not limit our analysis in this scenario to simply validating that the structure of the design and implementation are equivalent. Instead, we need to consider the way of working as introduced just before this slide, and then define required consistency checks based on that. And in addition to common structural checks, verifying, for example, that the components provide the designed interfaces, we can consider some structural aspects closer to the described behavior and verify, for example, that each state in each state machine is represented by some function in the code. So there are several techniques known for this kind of architecture validation, although it should be noted that we are not really interested in kind of generic architecture conformance rules, like each block should have a conforming class in the code or something like that. Instead, we are checking that the model and the code are consistent which means in particular that we check for three things. So one is absence. So the code should represent all the concepts defined in the system model that are relevant to the software. So there shouldn't be any unmatched model elements like blocks or ports that are then not represented down here in the code. And divergence, that's kind of the opposite. So the code should not represent more than what is defined in the system model. So we shouldn't have functionality defined in the code that is unknown in the system model. And then the last thing is contradiction. So the code should not contradict things that are defined in the system model. So if a function is defined in both artifacts, you want them to be for the same purpose too. And given the large gap between the model and the code, any approaches based on code generation and thereby kind of guaranteeing a consistency by construction are not really viable in this case. So we look at approaches that check consistency afterwards. They are kind of correct by detection. So among other approaches, you have, for example, reflection modeling, which is kind of similar to what we proposed. And the idea is that you model some hypothesis of the design. So the system model could be seen as something like that. And then you compare that to some representation of the code. But there needs to be a manual mapping between those representations by an engineer to know which elements are which. And other approaches have proposed incremental consistency checks, for example, based on navigation and traceability links between model elements and code. And also existing implementations for working with multiple artifacts, like Syndea, for example, they also require kind of manual linking between different artifacts, so to indicate which elements are the same or at least linked by the tool. A common required thing emerges from these approaches that we need somehow to map elements from the model to elements in the code. In fact, that's actually the kind of the biggest part of the work, because after having that, checking some rules is quite easy, but doing this manual linking takes a lot of time because there can be kind of thousands of model elements. And also this is something that is suspected to be kind of dropped the first under any kind of time pressure. So we have to ship this patch today, so let's ignore this kind of boring manual linking and let's forget about it for a while. And then of course it becomes hopeless to maintain this. So we want to provide some automated support for uncovering these traceability links within an existing MBSE project. So, but mapping the model elements to code parts is not so straightforward, because first, as said, there is a gap between the model and the code. So there may be some granularity differences where one element in the code may be implemented by several elements in the one element in the model may be implemented by several elements in the code. And second, we cannot just rely on name equivalents to match the elements across the different artifacts. For example, because there are different naming conventions between models and code. So many existing approaches, name equivalence is kind of assumed implicitly, but it's not really applicable in practice. Because what we encounter is that the set of code names are kind of inspired by their model counterparts, but they are not, they're certainly not equivalent. So in the best case, the difference is limited. For example, only spaces are replaced by underscores, but there are more difficult cases to handle in which long names are abbreviated in the code. For example, in this example, we have some model element named hardware monitor, and then in the code it's represented as HW_mon. So what we propose is to semi-automate the link discovery using a combination of steps. First, we create a dictionary to translate the most common abbreviations within the domain or within the company. And then the second step is to apply some rewrite rules according to the modeling or coding standard. So in this case, we would replace the spaces with underscores and remove capitals, for example. And then the final step, we would obtain some similarity score from comparing the resulting strings. And also, here we can take into account the type of elements. So you know from the way of working, for example, that a class name is not likely equal to a single state in a state machine. It would make more sense for that state to be mapped to a function name, for example. So the current status of this work is that we have a Rhapsody plugin that obtains names from model elements. And we have defined the required consistency checks as we discussed. And then the next step is to access the code and then do the remainder of the steps. So getting the names of code elements and then implementing the proposed translation approach to automatically link the elements. And finally creating some consistency checks using the created links. And then more future work involves the evolution of these created links, because obviously once you have created them, you're not done. So since both the model and the code are subject to changes all the time, the links also need to be updated. So new links may need to be created, or existing ones need to be updated or deleted. So that's what we plan to do during the next sprint. So for now, I will move on to the second sub-project, which is on consistency checking model variants and revisions with variants and revision of code components. So in this sub-project, we aim to enhance existing consistency checks and modeling practices to appropriately handle variants and revisions of both the model and the code components. As I said before, these two dimensions are kind of orthogonal to each other, but both need to be considered. So in other research, people have referred these to as software evolution in time and space, where they're talking about unifying version and variability modeling, variability management for software engineering. So what we've done in this project is we've created some example models to compare different ways of modeling product variants containing software components. And in these examples, we consider the open source Geneva system, which provides some middleware infrastructure for in-vehicle infotainment. And we use this example because it's using software components, and also there's some architectural similarity between this and the real system that we will not be able to publish things about. So it's good to have some working example that we can show things on. So this is a very small sample of parts of models showing two ways you could deal with modeling variants. So the first one is done according to the variant modeling with SysML approach, and this is VAMOS. And the other one is a UML component diagram in which different variants of the system are configured. So in this kind of dummy example, we have just numbered the alternative component. So instead of having only one, the normal logging component, the DLT, we consider here also the possibility of using the logging component DLT2. So these are kind of variants of the software components, and then the configurations that are shown in the bottom diagrams allow for various products to be created using this one model. So either you select a variant with DLT2, or in the other variant here, you have the variant with DLT, and it includes the NHM core, and then it would include there the variant with DLT. So this example does not yet show the second time dimension of revisions. So for that, the models, for example, could live in separate files such that you can then point to some identifiers. So in this situation, the most interesting architectural consistency check is to ensure that the code in the components does not violate the interface definitions as outlined in the system model. So in general, of course, unintended dependencies should be prevented. And at the same time, as in the other case, the checks should be somewhat forgiving, because of course you don't want to be blocked in developing something because some consistency check forbids you from doing something. So in the studied setting, in contrast to sub-project 1, here already some consistency checks are in place, and they do rely on some naming equivalence between interfaces and model elements. And they are limited to checking only this interface compliance that I talked about. And currently they are not variant aware. So currently creating variants is done by copying the entire project, and then that of course can make the maintenance quite a bit more difficult than it could be otherwise. So the current state of this work is that we have created these example models for the use case and have designed consistency checks that can deal with different configurations of the models. So the actual implementation of these checks is quite different depending on the way of modeling the variability, and even depending on the modeling tools in which you're working. We've also created the software build of the GNV platform such that we can compare the model and the code also to the resulting image. So far, a hidden challenge is that these different variants also require different configuration in the build tooling. So the GNV project uses this Yocto build system, and it contains several configuration files that you need to update as well if you want to choose one variant or the other one. So eventually, our goal is to be able to automatically select the correct build scripts from the configured current variant of the design model. So in summary, we are working on these two sub-projects, both related to model management, but in more broad sense, management of consistency between diverse development artifacts. And in both projects, the goal that we started from is to enhance the agility of model-based software and systems engineering. The first project considers the challenge of establishing and maintaining traceability links between parts of the model and parts of the code. And the other sub-project considers the challenge of managing these model variants and revisions at the same time. So in future work, in both cases, in addition to the future work that we mentioned per project, some additional interesting work is to study if we can learn from revision history in suggesting resolutions for failed consistency checks. For example, a particular type of interface violation can have been resolved in the same way multiple times in history, and then that could be maybe used to suggest a similar solution for some newly detected interface violation. So that concludes my brief overview of our project on managing inconsistent development artifacts. I think I've run out of time now, but please do contact us later if you have any questions, suggestions, or even ideas for collaborations or something. Thank you for your attention.
Thank you very much indeed. And I see that there was a question from Gernfors in the chat, but I think John already had it, answered it. But are there any questions? We might have time for 2 minutes left.
I will have a look at the question in the chat indeed.
Yeah. That was handled.
Okay.
That was handled that way. And I just have a question more from the software industry. Then people might draw UML models and then they forget about them. Have you seen similar behavior at Saab, or are they thankful to the models and actually look into them even?
Yeah, well, so the idea is that not only they use it to design the system now, but also they need to have those models later, because those products have an extremely long lifetime. So if you come back in 15 years and you want to understand the code base, they want to be able to look at the model instead of going through the code. So they don't forget about it.
Okay. Happy news for engineers.
That's good.
Yeah. So I suggest that we thank you with a virtual or distributed applause.